Good day everyone, and welcome to where we are putting together solutions for the subject of additional mathematics. And in this video we'll be looking at specifically the topic of kinematics for the first 5 years of the additional mathematics syllabus in CSEC. Don't forget to like the video and add any comments down below so we can help create other videos to assist you in whatever areas that you are struggling in. If you look at the description down below, it outlines the order we suggest that you go through the entire CSEC Add Maths syllabus in order for you to get a better grasp of the subject area. Let's take a look at the 4 major sections of this Add Maths syllabus, and this video will be specifically looking at section 3, which looks at introductory calculus. This is subdivided into differentiation and integration, which we have dealt with in a previous video. But there's a subtopic which comes off of these two, which is kinematics. So this video deals specifically with that. Kinematics is tested as one whole question worth 20 marks in paper 2. It looks at real-world applications of differentiation and integration, specifically dealing with the ST and VT graphs. And kinematics reminds us that S is equal to the integral of V dt and V is equal to the integral of A dt. If we look at the formula sheet, it states that S is equal to the integral of V, velocity, with respect to t, and velocity is equal to the integral of acceleration with respect to t, or vice versa. V is equal to dx dt, x or S is interchangeable for displacement, which is equal to x dot, and A is equal to d2x dt squared, which is equal to dv dt, and can also be written as x double dot. In the last section of the paper, number 7 is statistics and number 8 is kinematics, and students are given a choice to choose one out of 2 of them. Kinematics itself comes as number 8 for the 5 years. May 2012, number 8A. A car starts from rest at a point A, moves along a straight line reaching a velocity of 24 meters per second by a constant acceleration of 6 meters per second squared. The car maintains this constant velocity of 24 meters per second for 5 seconds and is brought to rest again by a constant acceleration of minus 3 meters per second squared, which means that it is decelerating until it comes to rest. Part 1. Draw a velocity time graph to illustrate the motion of the car. So let's bring up the axes, with the x-axis being represented by t, time, in seconds, and the y-axis, v, velocity, in meters per second. And let's put in the information. If we look at the information, we can see the car started from rest. So that means we're starting the graph at 0, and it moves along a straight line until it reaches 24 meters per second by a constant acceleration. So we can draw a green line sloping upwards from 0 to 24. And we do not know the time it took, so let's call that t1. In the second part of the travel, the velocity was constant for 5 seconds. So let's bring up a flat green line to show such, and that second time interval t2 is equal to 5. And in the third part, it is brought to rest again by a constant deceleration. So from 24, let's draw a green line coming down until it hits the axis where it stops. We'll call that time interval t3. Part 2. Determine the total distance traveled by the car. So the total distance traveled in a VT graph is the area under the graph. So if we can work out t1 and t3, we will be able to get the total length of the base. We know the total perpendicular height is 24, and we know the other vertical part is 5. And then we can use the area of a trapezium to work out the total distance traveled. So let's work out t1. V is equal to u plus at in the first phase of the graph, where v is the final velocity and u is the initial, and we can substitute accordingly. So the final velocity in the first phase of the graph was 24, is equal to 0 because it started from rest, plus 6t1 because the acceleration is indicated as 6 meters per second squared. As such, since 24 is equal to 61, t1 is equal to 4 seconds. So let's bring up a 4 there to indicate from 0 after 4 seconds that show the end of the first section. And we know it took 5 more seconds in the second interval, so that means it will be 9 seconds at the end of t2. And for the third phase of the travel, v is equal to u plus 80, the final velocity is 0, the initial velocity is 24, and the acceleration is minus 3. So we can substitute 0 is equal to 24 plus minus 3t3. We can carry the t3 across, that will be equal to 24, so t3 is equal to 8 seconds. So the total time taken will be 9 plus t3, which was 8, so 9 plus 8 is 17 seconds. So now we can find the area of the trapezium. S is equal to half a plus b by h, where a and b are the parallel sides. So we can substitute. So S is equal to half by 5, which is t2, plus 17 times 24, the perpendicular height. Using our calculators, it works out to be the total distance of 264 meters. Part 3. A second car moving at a constant velocity of 32 meters per second drives past point A 3 seconds after the first car left point A. Calculate the length of time after the first car started that the second car meets it. Assume that the cars meet during the time when the first car is moving at a constant velocity. That means in the second phase of travel. So if we consider that the distance traveled by the first car S1 is equal to the distance traveled by the second car S2, in order to work out the distance traveled by the first car, we know it was the distance traveled in the first phase, which is the triangle, which is SA, plus a certain distance traveled in the second phase, not quite the whole rectangle. So let's work out for SA. SA is equal to UT plus a half AT squared. And we know it started from 0, so U is equal to 0, plus a half times the acceleration is 6 times the distance is 4 squared. So SA is equal to half times 6 by 4 squared. 4 squared is 16. Half of 16 is 8. 8 6 is 48. The total distance traveled by S1 will be SA, the distance traveled in the first phase, plus a rectangle. And the area of a rectangle is length by breadth, which is 24 times t minus 4. It's not the total time taken, because 4 seconds was used up in the first phase. And that will be equal to 32 times t minus 3. And this is because it started 3 seconds later, and that is equal to S2. And S2 is the distance traveled by the second car. We can bring that up as a blue rectangle because it's traveling at a constant velocity, and the area under that constant velocity is a rectangle. And the area of a rectangle will be length by breadth, which is 32 times, what's the base? Not the whole time t, but t minus 3, because it started 3 seconds later. So if we look at this whole line, we have one unknown, which is t, so we can solve for that. Expand the bracket, so it will be 24t minus 24 by 4 is 96, is equal to 32 times t is 32t minus 32 times 3, which is 96. So let's bring all the numbers on one side and all the t on the other side. So 48 plus 96 minus 96 is equal to 32t minus 24t. So that will give us 48 is equal to 8t. So t is equal to 6 seconds. So the time at which the two cars meet will be 6 seconds after the first car left. May 2012, number 8b. A particle moves in a straight line with the acceleration given by a is equal to 5t minus 1 meters per second squared at any time t seconds. When t is equal to 2 seconds, the particle has velocity 4 meters per second and is 8 meters from a fixed point O. Determine, part 1, its velocity when t is equal to 4. So if we want to find velocity, we know velocity is equal to the integral of a with respect to t. So we can substitute. So v is equal to the integral of 5t minus 1. And you can see this is an indefinite integral. So when we integrate, we will get c, the constant of integration within the answer. So v is equal to 5 t squared on 2 minus, when we integrate 1, it will give us minus t plus c1, the constant of integration. And we can solve for that because we know when t is equal to 2, v is equal to 4 meters per second. So if we substitute for v and t, we can find for c1. So let's do that. 4 is equal to 5 over 2 by 2 squared minus 2 plus c1. And 2 squared is 2 2s are 4. So this gives us 4 is equal to 5 times 2 squared is 4. 5 4s are 20 divided by 2. 2 into 20, 10 minus 2 plus c1. So 4 is equal to 8 plus c1. If you carry the 8 across, it will be 4 minus 8. So minus 4 is equal to c1. As such, the equation for the velocity is equal to 5t squared on 2 minus t minus 4. And we want to know the velocity when the time is equal to 4. So we can substitute. So let's rewrite the equation. V is equal to 5 on 2, t squared minus t minus 4. And when t is equal to 4, v is equal to 5 on 2 by 4 squared minus 4 minus 4. And 4 squared is 16. 2 into 16, 8. 8 5s are 40. 40 minus 8 is 36. 36 minus 4 is 32. So the velocity is 32 meters per second when the time is 4 seconds. And determine for part 2 is displacement from O when t is equal to 3. So what we want to find is S. And S is equal to the integral of v dt. And we worked out v in part 1. So we can substitute S is equal to integral of 5 on 2t squared minus t minus 4 with respect to time. So that will give us 5t cubed on 2 by 3 minus a half t squared minus 4t plus c2. A second constant of integration. When t is equal to 2 seconds, s is equal to 8 meters. So if we substitute, 8 is equal to 5 on 6 by 2 cubed minus a half by 2 squared minus 4 by 2 plus c2. So we can solve for c2. So 8 is equal to 2 cubed is 8. 8 5s are 40 over 6, which is 20 over 3. Minus a half of 2 squared, a half of 4 is 2. Minus 4 2s are 8 plus c2. Using our calculators, c2 works out to be 34 over 3. As such, the general equation for s is equal to 5 6 t cubed minus a half t squared minus 4t plus 34 over 3. And now that we know that equation, we want to solve it for when t is equal to 3 seconds. So if we substitute s is equal to 5 on 6 by 3 cubed minus a half by 3 squared minus 4 by 3 plus 34 over 3. 5 times 3 cubed, which is 27 over 6. 3 into 6, 2. 3 into 27, 9. So 5 9s are 45 over 2 minus a half of 9 or 9 over 2 minus 4 3s are 12 plus 34 over 3. So if we use our calculators, so that will give us S, the displacement when t is equal to 3 seconds, is 52 over 3 meters. May 2013, number 8A, a particle starts from rest and accelerates uniformly to 20 meters per second in 5 seconds. It continues at this velocity for 10 seconds. It then accelerates again uniformly to a velocity of 60 meters per second in 5 seconds. The particle then decelerates uniformly until it comes to rest 15 seconds later. A. Part 1. On the graph paper provided, draw a velocity time graph to illustrate the motion of the particle. So let's look at the graph. Let's underline the first important thing. It starts from rest. So that means your graph is starting at 0 meters per second. And then it accelerates uniformly, so it's going in a straight line. It's increasing to the right to 20 meters per second in 5 seconds. So we can draw that first green line sloping up to the right. And then what happens? It continues at this velocity for 10 seconds, so it remains constant. So from 5 seconds, it remains horizontal until it reaches 15 seconds. 5 and 10 is 15. Then what happens? It accelerates uniformly again, so it's sloping up to the right to a velocity of 60 in 5 seconds. So from 15 seconds to 20 seconds, it went up. The particle then decelerates uniformly, which means that it's slowing down until it comes to rest 15 seconds later. So we had 20 seconds, and if we add 15, that'll be 35 seconds. So it'll slope straight down until it reaches 0 again. Part 2. From your graph, determine A. the total distance in meters traveled by the particle. So since this is a VT graph, the total distance is simply the area under the graph. So this will give us a trapezium and a triangle. So the total distance will be the area of the trapezium plus the area of the triangle. And let's use our formulas, which is a half a plus b by h plus a half times base by height. And let's substitute accordingly. So it will be a half times what is a and b, the parallel sides in the trapezium. So the higher horizontal side moves from 5 to 30, so that's 25. And the x-axis is 35. So a half by 25 plus 35 times what's the perpendicular height? 20. That's for the trapezium. And for the triangle, a half times what's the base of the triangle? 15 to 30 is 15. Times the perpendicular height, it moves from 20 to 60, so that's 40. So we can work that out. A half times 20 is 10, 10 times 25 plus 35 is 60, so that will give us 60 by 10, 600. A half of 40 is 20, 20 by 15 is 300. So the total distance is 900 meters traveled. Part B, the average velocity of the particle for the entire journey. So the average velocity will be the total displacement divided by the total time. And the total displacement is 900. And the total time taken is 35 seconds. So 900 divided by 35 is 25.7 meters per second. May 2013, number 8b. A particle travels in a straight line in such a way that after t seconds, its velocity, v, from a fixed point O is given by the function v is equal to 3t squared minus 18t plus 15. Calculate, part 1, the values of t when the particle is instantaneously at rest. So let's write our formula. V is equal to 3t squared minus 18t plus 15. And if the particle is at rest, that means the velocity is 0. So we can write that 0 is equal to, and we can factorize that quadratic, so it will give us 3t minus 3 by t minus 5. So either the first brackets, 3t minus 3 is equal to 0, which means 3t is equal to 3, so t is equal to 1 second, or t minus 5 is equal to 0, so t is equal to 5 seconds. As such, the particle is at rest when t is equal to 1 second and when the time is 5 seconds. Calculate for part 2 the distance traveled by the particle between 1 second and 3 seconds. So we know that if we want to find the distance, s, that will be the integral of v with respect to t between limits a and b. And in this particular case, s is equal to the integral of 3t squared minus 18t plus 15, because we know what v is, between the limits of 1 and 3, because that's the time interval that we want to find the distance. So now what do we have? We have a definite integral. So when we integrate 3t squared, that will give us 3t cubed over 3, and of course the 3's will cancel, minus 18t squared over 2 plus 15t plus c1, the constant of integration. Some people will leave it out because it will cancel off in the end. So if we substitute now, it will give us, since the 3 is cancelled, 3 cubed minus 18 on 2, which is 9 by 3 squared, plus 15 by 3, plus c1, minus 1 cubed minus 9 by 1 squared, plus 15 by 1, plus c1. The c1, so the constants of integration, cancel. So if we use our formulas, the top line will give us 3 cubed is 27, minus 9 by 9 is 81, 27 minus 81 is 54, plus 15 3s are 45. 54 minus 54 plus 45 gives us minus 9. Minus 1 cube is 1, minus 9 ones are 9. 1 minus 9 is minus 8, plus 15 is 7. So minus 9 minus 7. As such, the distance traveled by the particle between the time 1 second and 3 seconds is minus 16 meters, meaning that it moves 16 meters in the opposite direction. Calculate part 3, the value of dv dt when t is equal to 2 seconds. We know v, so dv dt, let's differentiate that, will give us 60 minus 18. And when t is equal to 2, we can substitute. dv dt is equal to 6 by 2 minus 18, 6 2 are 12, minus 18 is minus 6. So the velocity is minus 6 meters per second when the time is 2 seconds. And for part B, calculate the value of dv/dt when t is equal to 3 seconds. So dv/dt, we already worked that out, and we can substitute for t is equal to 3, will be 6 by 3 minus 18. 6 3s are 18 minus 18 is 0. That means that dv/dt, or the acceleration, is 0 when the time is 3 seconds. Last part of the question, calculate part 4. Give an interpretation for the value in 8b part 3a. We know that dv/dt is equal to minus 6 meters per second. So this is indicating that the particle is slowing down with a deceleration of 6 meters per second. And give an interpretation for the value of 8b part 3. So dv/dt is equal to 0, which means that the acceleration is 0, or the particle is at a constant velocity. May 2014, number 8a, figure 2 below, not drawn to scale, shows the motion of a car with velocity v as it moves along a straight road from point A to point B. The time t taken to travel from point A to point B is 90 seconds, and the distance from point A to point B is 1,410 meters. Part 1. What distance did the car travel from point A towards point B before starting to decelerate? So what that is asking us for is that area A. So it's asking us for the distance traveled in the first 30 seconds, and the distance traveled in a VT graph is the area under the graph. So let's bring up that as a blue rectangle. So the area of that rectangle A is length times breadth, which is 30 times 25, which is equal to 750 meters. Part 2. Calculate the deceleration of the car as it goes from 25 meters per second to 10 meters per second. So the total distance is equal to area of A plus area of B, which is trapezium, plus area of C, which is the rectangle. And let's substitute what we know. So 1,410 is equal to area of A, which we worked out in part 1 as 750, plus the area of B, which is a half A plus B by H, plus the area of C, which is length by breadth. And if we substitute, 1,410 is equal to 750 plus a half times what are the parallel sides of that trapezium, 10 plus 25 times T1, because we do not know that time, plus the area of C, which is 10 times 60 minus T1. And remember, the total time taken was 90 seconds, and up to the end of A was 30 seconds. So what we did was subdivide the remainder 60 seconds into T1, the time for deceleration, and 60 minus T1, which will be where it continued at a constant velocity. So if we notice on that line, we only have one unknown, T1, so let's solve for that. So 1,410 is equal to 750 plus a half times 35, which is 17.5 T1, plus 10 by 60 is 600 minus 10 T1. If we add 750 plus 600, it will give us 1,350. We carry it across. 1,410 minus 1,350 is equal to 60. On the left hand side will be equal to 17.5 T1 minus 10 T1, which is 7.5 T1. So T1 is equal to 60 divided by 7.5, which is 8 seconds. As such, the acceleration within that time period would be the change in velocity divided by the change in time. So the change in velocity is equal to minus 15 because it's decelerating, and the change in time, which is T1, is 8 seconds. So minus 15 over 8 will give us minus 1.875 meters per second squared. Part 3. For how long did the car maintain the speed of 10 meters per second? So that will be 60 minus T1, which is 60 minus 8, which works out to be 52 seconds. And the last part, part 4, from point B, the car decelerates uniformly, coming to rest at a point C and covering a further distance of 30 meters per second. Determine the average velocity of the car over the journey from point A to point C. Shows the velocity going downwards from 10 meters per second until it comes to rest. And what do we know? We know the area of that triangle, or is the distance traveled, and the area of a triangle S is equal to a half base by height, and s is equal to 30. So 30 is equal to half times t2, that time taken, times 10. So half of 10 is 5, 5 divided by 30 is 6. So the time taken, t2, is 6 seconds for it to decelerate. So the average velocity is the total displacement divided by the total time taken. So the total displacement is 1,410 plus 30 divided by total time taken is 90 plus 6, 96. And that works out to be 15 meters per second. So that means that if we consider the car moving at 15 meters per second from point A until it reaches point C over this 96 seconds, it will still cover the same distance as what actually happened on the graph. May 2014, number 8b. A particle travels along a straight line. It starts from rest at a point P on the line, and after 10 seconds, it comes to rest at another point Q on the line. The velocity v meters per second at time t seconds after leaving P is v is equal to 0.72 t squared minus 0.096 t cubed for the first 5 seconds, for the time interval from 0 less than or equal to t to less than or equal to 5, and there's a different velocity equation, v is equal to 2.4 t minus 0.24 t squared for 5 less than or equal to t, which is less than or equal to 10, which means for the second 5-second interval. At maximum velocity, the particle has no acceleration. Part 1. Find the time when the velocity is at its maximum. So let's consider the first equation. v1 is equal to 0.72 t squared minus 0.096 t cubed. And if we want to get the velocity at a maximum, then we want to find dv dt. d dt of v1 is equal to 1.44 t minus 3 times 0.096, which is 0.288 t squared. And we know for maximum, d dt of v1 is 0, so we can substitute 0 is equal to, we could factorize that quadratic by pulling out 1.44t, and that would be left in brackets by 1 minus 0.2t. And in order to solve for this quadratic, either t is equal to 0 or 1 minus 0.2t is equal to 0, which means if we carry it across and solve for t, t is equal to 5 seconds. And since it told us that it starts from rest, then the maximum velocity could not be when time is 0, but when time is equal to 5 seconds for the first time interval. So if we bring up a graph, just for students to get an idea of this cubic equation, we can see with that red line there that there's a maximum when t is equal to 5 seconds. And let's try for v2, the second time interval, which is 2.4t minus 0.24t squared. If we want to find the maximum at this point, then we have to find the differential of v2, which works out to be 2.4 minus 2 times 0.24, which is 0.48t. And for maximum, of course, differential is 0, so we can substitute 0 is equal to 2.4 minus 0.48t. And if we solve for that as well, that will also give us time is equal to 5 seconds. So in both cases, v1 and v2, the maximum is when time is equal to 5 seconds. And if we bring up a second graph to show what that quadratic equation looks like, we can see it also hits the maximum when t is equal to 5 seconds. Part 2. Determine the maximum velocity. So we can substitute t is equal to 5 seconds into either one of the equations. So let's write the equation. v1 is equal to 0.72 t squared minus 0.096 t cubed. And if we substitute for when time is 5, because that's when the maximum velocity occurs, then v1 is equal to 0.72 by 5 squared minus 0.096, 5 cubed, which works out to be, using our calculators, v1 is equal to 6 meters per second. And we don't need to do it for the second time interval, but we can do it as well just to show that v2 is equal to 2.4 t minus 0.24 t squared. And when we substitute with time is 5, it will give us 2.4 by t, which is 12 minus 0.24 by 5 squared. And that works out to be 6 meters per second in the same case. And that is supported by our sketch. Part 3. Find the distance moved by a particle from P, that's the starting point, to the point where the particle attains its maximum velocity. So let's bring that up as a blue area so we can see what it looks like. So what they're really asking us is to find the area under this VT graph between the limits of 0 and 5. For the first equation, because that's the equation that covers the first time interval of 5 seconds, then we say S is equal to the integral of V1 with respect to t between the time intervals 0 to 5. And if we substitute, S is equal to the integral of 0.72 t squared minus 0.096 t cubed dt between 0 and 5. So that gives us S is equal to 0.72 divided by 3 t cubed minus 0.096 divided by 4 t fourth between 0 and 5. And we can substitute accordingly for 5 and 0. So it will give us 0.72 divided by 3 times 5 cubed minus 0.096 divided by 4 by 5 to the fourth minus 0.72 divided by 3 by 0 cubed minus 0.096 divided by 4 by 0 to the power 4. Of course, everything substituting with 0 in it goes out to be 0. So we're really just working on the first part of the substitution. So it gives us 30 minus 15. As such, the total distance moved in the first 5 seconds is 15 meters, which is the area of that blue shape. May 2015, number 8a. A particle moves in a straight line, has a velocity of 3 meters per second at t is equal to 0, and 4 seconds later, which means t is equal to 4, its velocity is 9 meters per second. Part 1. On the answer graph sheet provided as an insert, draw a VT graph to represent the motion of the particle. So if we're considering that it's moving in a straight line, and at time 0, it's 3 meters per second, that means we're starting on the y-axis at 3, and we're increasing steadily until it's 9 meters per second when the time is 4. Part 2, calculate the acceleration of the particle. So the acceleration in a VT graph is the gradient of the graph, and that's simply the change in v over the change in t. The change in velocity moved from 3 to 9, so the change in velocity is 6, and the change in time is 4. So 6 over 4 is equal to 1.5 meters per second squared. Part 3, determine the increase in displacement over the interval t is equal to 0 to t is equal to 4. So we want to find the increase in displacement. So the area under the graph is a trapezium, which we'll bring up in yellow there. So to find the area, S is equal to half a plus b by h. So a half by 3 plus 9 by 4. So half of 4 is 2, 2 by 3 plus 9 is 12, 2 12s are 24. So the increase in displacement is 24 meters. May 2015, number 8b. A particle moves in a straight line so that t seconds after passing through a fixed point O, its acceleration a is given by a is equal to 3t minus 1 meters per second squared. The particle has a velocity v of 4 meters per second when t is equal to 2, and its displacement s from O is 6 meters when t is equal to 2. Find, part 1, the velocity when t is equal to 4. So let's recall what information we have that is helpful. We know the acceleration, a, which is 3t minus 1, and they want us to find the velocity. Velocity is equal to the integral of a with respect to t. And if we substitute for a, it will be v is equal to the integral of 3t minus 1 dt, which gives us 3t squared on 2 minus t plus c1, the constant of integration. And we want to find velocity when t is equal to 4. So right now we have 3 unknowns, v, t, and c1. And at the point where the velocity is 4 meters per second, the time is 2. So if we substitute for 2 of those variables, then the only unknown will be c1, and we can solve for that. So when t is equal to 2, v is equal to 4, and we can substitute. So 4 is equal to 3 on 2 by 2 squared minus 2 plus c1. So 4 is equal to 2 squared, 2 2s are 4, 2 into 4, 2, 2 3s are 6, minus 2 plus c1. So 6 minus 2 is 4, and if we carry it across to the left-hand side, 4 minus 4 is 0. So C1, the constant of integration, is 0. As such, the formula for V is equal to 3 on 2 t squared minus t. And we can now solve for V when t is equal to 4. So V is equal to 3 on 2 by 4 squared minus 4. 4 squared, 4 4s are 16. 2 into 16, 8. 8 3s are 24. 24 minus 4. So the velocity when the time is 4 seconds is 20 meters per second. Part 2. Find the displacement of the particle from O when t is equal to 3. So they're asking us to find S. And let's recall that S is equal to the integral of V with respect to t. And worked out V in part 1. So S is equal to integral of 3 on 2 t squared minus t dt. When we integrate t squared, it will give us t cubed over 3. 3 will cancel with 3, so that gives us a half t cubed minus a half t squared plus c. And let's call this second constant of integration c2. Not to be mixed up with the first constant of integration c1. So we have 3 unknowns here. And in order to find for c2, let's find a position where we know the s and t values. So let's recall from above, from O is 6 meters when t is equal to 2. So at that point, we know s and t. So let's substitute. So when t is equal to 2, s is equal to 6 meters. So substituting, it will give us 6 is equal to a half by 2 cubed minus a half by 2 squared plus c2. So now we can find for c2. So 6 is equal to a half by 2 cubed is 8. A half of 8 is 4 minus a half of 4, which is 2, plus c2. 4 minus 2 is 2. Carry that across. 6 minus 2 is 4. So 4 is equal to c2. As such, the equation of the displacement of the particle S from O is equal to a half t cubed minus a half t squared plus 4. And we can solve now for S when t is equal to 3. So let's substitute. S is equal to a half by 3 cubed minus a half by 3 squared plus 4. 3 cubed is 27, so that will give us 27 over 2 minus 9 over 2 plus 4. 27 minus 9 is 18 over 2, which is 9. 9 plus 4 is 13. So it tells us that the displacement of the particle from O when the time is 3 seconds is 13 meters. May 2016, number 8A. A motorist starts from a point X and travels 100 meters due north to a point Y at a constant speed of 5 meters per second. He stays at Y for 40 seconds and then travels at a constant speed of 10 meters per second for 200 meters due south, which means in the opposite direction, to a point Z. Part 1. On the following grid, draw a displacement time graph to display this information. So if we look at the grid and we put in the values on the x and y axes, the x-axis being time and the y being displacement, let's take the direction heading north as positive. So the first part tells us he went 100 meters due north at a constant speed of 5 meters per second, which means he took 20 seconds for that to happen. So we can draw a green line starting with the displacement being 0, going upwards, meaning going to plus 100 in 20 seconds. And then what happens? He stays there for 40 seconds, meaning he's at rest. So the displacement does not change. So you can draw a flat line from 20 seconds going across 40 more seconds to 60. And then he goes due south. So he's going in the opposite direction, a distance of 200 meters. So if he was 100 meters due north and the displacement is such that he moves 200 meters due south, then he will end up at minus 100. And how long did that take him? He was moving at 10 meters per second. So 200 divided by 10 will give us 20 seconds. As such, he moved from point Y to point Z in 20 seconds. So from 60, it'll go to 80, so we can draw a line to indicate such. Part 2. Calculate the average speed for the whole journey. So average speed is equal to total distance moved over total time taken. The total distance moved is 100 in the first phase, plus 0 in the second phase, plus 200 in the third phase. Divided by total time taken is 20 seconds in the first phase, 40 seconds in the second phase, plus 20 seconds again in the third phase. So it will give us 300 divided by 80, which is 3.75 meters per second. That's the average speed. And part 3, calculate the average velocity for the whole journey. So the average velocity will be the total displacement divided by total time taken. So the total displacement is, it went up 100 and then went in the opposite direction 200. So 100 minus 200 over the same time 20 plus 40 plus 20 for the 3 phases. So that will give us minus 100 over 80. So the average velocity is minus 1.25 meters per second. May 2016, number 8b. A particle starting from rest travels in a straight line with an acceleration a, given by a is equal to cos t, where t is the time in seconds. Part 1. Find the velocity of the particle in terms of t. So v is equal to the integral of a with respect to t. And we can substitute for a. So v is equal to the integral of cos t with respect to t. So v is equal to sine t plus c1, the constant of integration. So we don't know v, t, and c1. So let's look at the question again. It says the particle is starting from rest, which means when t is equal to 0, v is equal to 0. So we can substitute accordingly. So 0 is equal to sine 0 plus c1, and sine 0 is 0. So that means c1 is equal to 0. So the equation for the velocity is such that v is equal to sine t. Part 2. Calculate the displacement of the particle in the interval of time t is equal to pi to t is equal to 2 pi. So we know s is the integral of v with respect to t within that interval pi to 2 pi. So what we're finding here is a definite integral. And we know v, we worked that out in part 1, so we can substitute. S is equal to the integral of sine t with respect to t between pi and 2 pi. So s is equal to minus cos t between those limits. And if we substitute, it's going to give us minus cos 2 pi minus cos pi. And cos 2 pi, same as cos of 0, is equal to 1. So the first brackets will give us minus 1 minus, and the second brackets, minus cos pi. And cos pi is minus 1. So that'll be minus 1. As such, it gives us minus 1, which is minus 2 units. So the displacement of the particle between that time interval of pi and 2 pi seconds is minus 2 units. We've now come to the end of CSEC past paper questions in the topic of kinematics. In our last video, we looked at past paper questions from 2012 to 2016 for introductory calculus. And in this video, for the same 5 years, we looked at kinematics. In our next video, we will be combining the two topics for the years 2017 until 2022. Don't forget to look at the description down below in order for you to get a better grasp of the order we suggest to go through the entire CSEC Add Maths syllabus.